Black holes have a reputation for ending things. They swallow light, crush matter, and mark the point where physics seems to give up. For decades, they've dominated the public imagination as the ultimate cosmic monsters.
Black hole is a region of space and time where the strength of gravity is so high that light has no path to get out of the object. All paths through space-time curve back in.
But black holes are only one side of a much stranger story. On the other side lie concepts that feel less like astronomy and more like philosophy made physical: white holes and wormholes. They exist not as confirmed objects we can point to in the sky, but as serious solutions to Einstein's equations that stretch our understanding of reality itself. A white hole is, in simplest terms, the mathematical opposite of a black hole. If a black hole is a region of space-time that nothing can escape from, a white hole is a region that nothing can enter.
Lurking in the depths of the mathematics of Einstein's general relativity is an object even stranger than the mysterious black hole. In fact, it's the black hole's mirror twin, the white hole.
Matter and energy can come out, but never go in. From the outside, a white hole would appear to be spewing material and radiation, seemingly without any source. It wouldn't form from collapsing stars. It wouldn't grow by feeding. It would just exist, ejecting matter as if time itself were running backward. That backward time aspect is not a metaphor. In the equations of general relativity, a white hole is what you get when you reverse the direction of time for a black hole solution. Mathematically, it works. Physically, it creates problems.
That makes a white hole a region of outward-flowing space-time. It also has an event horizon, but that horizon prohibits entry, not exit. Nothing outside a white hole can ever enter, and everything inside must be ejected.
The universe, as far as we can tell, prefers increasing entropy. Things fall apart. They don't spontaneously organize themselves and explode outward in reverse. A white hole appears to violate that preference, which is one reason many physicists are skeptical of their existence. And yet, the equations don't forbid them. They allow them, which leaves us in an uncomfortable place where mathematics says possible, but observation says we've never seen anything like this. If a white hole did exist, it would be violently unstable. The moment even a single particle tried to fall in, the structure would collapse. That makes white holes extraordinarily difficult to form and even harder to maintain. They would have to be born in a very specific way, under conditions we don't yet know how to produce naturally. Some theories suggest they could be connected to the birth of the universe itself, emerging from a prior cosmic phase or a bounce rather than a bang. That idea leads directly into wormholes. Wormholes are shortcuts through space-time, tunnels connecting distant regions of the universe or even different universes altogether. In theory, a wormhole could link two points so far apart that traveling between them normally would take thousands of years, while the wormhole would allow passage in seconds. Like white holes, wormholes emerge naturally from Einstein's equations. And like white holes, they come with strings attached. The simplest wormhole solutions are not stable. They pinch off too quickly for anything to pass through. To keep a wormhole open, physics requires something exotic, matter with negative energy density. Not just energy we don't know how to harness, but a form of matter we're not even sure exists. Without it, a wormhole collapses faster than light could cross it. This is where science fiction enters the conversation, but it doesn't fully take over. Physicists take wormholes seriously enough to study their properties, limits, and implications. They ask what kind of universe would allow them, what laws would need to be bent or extended, whether quantum effects could provide the stabilizing influence classical physics lacks. Interestingly, black holes, white holes, and wormholes may not be separate ideas at all. In certain models, they're connected. A black hole could, in theory, be linked to a white hole elsewhere in space-time. Matter falls into the black hole, disappears from our universe, and emerges from a white hole in another region, or another universe entirely. To an outside observer, the black hole absorbs. Somewhere else, a white hole emits. There is no evidence that this happens, but the mathematics doesn't rule it out either. Modern theories of quantum gravity have revived interest in these ideas. Some researchers propose that what we call black holes may not end in singularities at all. Instead, quantum effects could prevent infinite collapse, causing matter to rebound and emerge as a white hole-like structure. From our perspective, the black hole lasts trillions of years. From the inside, the transition could be brief. Time behaves very differently under extreme gravity. This reframes black holes not as cosmic dead ends, but as transformative regions, not destroyers, but bridges. Even if those bridges are one-way or inaccessible, the implication is profound. It suggests the universe recycles information in ways we don't yet understand. Wormholes add another layer of discomfort. If traversable wormholes exist, they raise questions about causality itself. Depending on how they're configured, wormholes could allow travel not just across space, but across time. That opens the door to paradoxes physics hates. Many scientists suspect that some unknown principle prevents this, preserving cause and effect. But again, we don't know for sure. What makes all of this more than idle speculation is how closely it ties into real research. Black holes are no longer theoretical. We've imaged them. We've detected their mergers through gravitational waves. The fact that white holes and wormholes arise from the same framework means they can't be dismissed outright. They're not fantasy. They're unresolved consequences of a theory that otherwise works extremely well. There have even been proposals that certain mysterious cosmic events, brief, intense bursts of radiation with no obvious source, could be signatures of white hole-like phenomena. These ideas are controversial and far from accepted, but they illustrate how the boundary between speculation and testable science is slowly shifting. At a deeper level, white holes and wormholes force us to confront how little we understand about time. Physics equations often work just as well backward as forward. Our experience of time flowing in one direction may be an emergent property, not a fundamental rule. If that's true, then objects that look impossible from our perspective might be perfectly natural from a more complete view of spacetime. The unsettling truth is that black holes may be the most understandable members of this trio. White holes and wormholes sit at the edge of knowledge, where mathematics, physics, and philosophy blur together. They challenge not just what we know, but how we think we know it. Whether these objects exist in reality or remain mathematical ghosts, they serve an important purpose. They expose the cracks in our understanding. They show where our theories are powerful and where they're incomplete. They remind us that the universe is under no obligation to match our intuitions. Beyond black holes lies a stranger landscape, one where matter can emerge from nowhere, where space folds in on itself, where time may not be as one-directional as it feels. We may never travel through a wormhole or witness a white hole erupting into existence. But the fact that the laws of physics even allow us to imagine such things is a sign that reality is far more flexible and far more unsettling than it appears.
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery, click the video right here.